Now, so moving further to the unanswered question of the day 3 section of the summer training school. So the first question I say, which application are you using to present? Then, so we answered, we present the use of course Zoom, of course supported with the appropriate PowerPoint presentation. And we also made use of some weka for display and also for that presentation that were used. Those are the applications majorly that we do employ in our weekly program and also in the summer school. What is the yardstick of dividing the data to training set and testing sets? Yeah, so I think this question will take us to quickly look into why do we divide data? How do we divide the data? You see, we did mention, if we remember, I will take us memory lane. That is how to check generalization ability of models. You see, the reason for dividing the data is we could have just given all the data sample to the algorithm so that you give like 1,000 data, I give everything to the system, but then it will train itself. There will not be way to know. There will be no way to know that is the training going to work for others or not? And that was why we gave ourselves what we refer to as the hypothesis for the machine learning hypothesis. That if it works on enough data, it will work on unseen samples. So this is the essence of saying we want to check the generalization ability of the models. You see, once you build the model, we want to see if it's going to work on the unseen data, because the essence is future. See, if you are able to train a system that can detect if somebody is having depression or not, and then next time we can use that model that has been built to predict if somebody is likely going to have depression. We don't need to wait. So to see that is it going to work for cases that are coming in future, that is why we need to check for the generalization ability of the model. And there are two major ways of dividing data. The first one, we refer to it as the holdout method. Holdout method, holdout. This is when you hold out, means you pattern your data into 2 or 3 portions. You give one to the algorithm for training, you keep others away. You hold it out, holdout method, keep it away. So this holdout method has 2 options. With the first option is you divide it into 3. And the second one is you divide it into 2. Let's start with these 2. This is the common one. You see, you divide your data into 75% for training. They gave me like a 1,000 data sample. I use 750 to train my model, to build my model. And I use the remaining 25, which is 250, to do the testing, to check if what I've trained here is working fine. But sometimes if your data is sizable, which is a relative term, you can divide it into 3. I can use 70% for training, 15 for validation, another 15 for final testing, which they call the publication set. So it does depend on the size of your data. But if your data is sizable, 3,000, 4,000, 5,000 or more, then you have the capability to divide into 3. See, use one for training, use this one for testing. So, and then you keep this one for another final validation later on of test or publication testing, as the case may be. Either you use this or this, you are correct. However, when your data is very few, you might not be able to go for 3. Even 2 sometimes might not be possible. In that case, we go for the second type, which we call n-fold crowd validation. N-fold crowd validation. In this case, you cannot price this holdout. Usually it is done when the data is few. Few sample. I know somebody want to ask me, what is few? Few is a relative term. What is few in one feed might not be few in another feed. There are some feed where you have a lot of data availability. The more the data samples, the better, by the way. But sometimes we are limited by the availability. So in that case, we go for n-fold. What is n-fold? Let's take, for example, this is 10-fold crowd validation. In n-fold, you divide your data into 10 places. Let's say I have like 100 samples, only 100. I don't have 1,000. I don't have 2,000, just 100 samples. I divide into 10, 10. This is 10, 10, 10, 10. So each of these fold is made up of 10 samples. All of them combined together make 100. Now, so when I'm building my model, I will use the entire data from 2 to 10 fold. I will add all of them together. That's going to be like 90. Use it for training, and I'm going to test it using this only one. Next stage, I'll train another using another 90, but this time around, 2 was part of the training. I'll make it to be the testing now. This is not going to be part of the training. This was part of the testing before. I bring it back to become part of the training. You can see here, training, training. I'm going to use this number 1 and 3 to 10, which is 90 in number. I use them for training, and I use this for testing. I keep shifting the window until each of the fold participate in the testing process. You can see it keep moving until this is used for testing. This has been part of training always, but the last stage is going to be part of the testing. It means I'm going to have 10 results. Result number 1, result number 2. So I'm going to add everything together. I'm going to find the average. You see, maybe here I'm getting 90% accuracy here, 75, 79, up to the 10th one. Maybe here I'm getting 90% or 91%. Add everything together, divide by 10. That will give you the average performance for the 10-fold cross-validation. This is the second way to partition our data. But the good news, sometimes your data is not even up to 100. So using 10-fold does not arise. You can use 2 folds. You can use 3. You can use 4, 5, 6, 7. You can use more than 10, by the way. However, so if you're having like, maybe someone gave you data of like 15, just 15 samples, holdout method is not an option because it's too small. How many are you going to use for training if you use holdout? So we go for like 3 folds. It means each fold is going to have 5 samples. Somebody might even say 3 folds is too much. Okay, you go for 2 folds. So this is where the idea of n-fold cross-validation arises. So in that case, we use n-fold cross-validation to check. It's a kind of a proof of concept that is this system going to work? So that if it works for this kind of 15 samples, we train it using 3-fold, and we found out that we are getting like maybe 92% accuracy finally. Wow. Then we can then tell our client that it has prospect. That's a good prospect for this particular work. So you can go ahead and spend money and get as many data sets as possible for us. Let us build machine learning for your system so that you can use it to predict future case. So when they now finally get enough data, then we will now go back and use this idea of holdout, because with the one that they're going to use in their company that will be used in real life, it has to be trained using the holdout method, because we want to train it with a lot of data. So like 70% for training and the remaining one for testing and validation. But before we get the data that is enough, then we can be using n-fold cross-validation to show, to tell people the proof of concept that yes, it can actually work. So this is how we generalize. We check generalization ability, by the way. And that is what the question is trying to ask. So in what yardstick are we going to use to divide the data to training set and testing set? So it's a function of the size of your data set. If the size is reasonable enough, we don't need to be specific with what is reasonable. It depends on the area. Yeah. But anything less than 20, 30, 40, divided into 2, training and testing will really not be all right. So we go for n-fold cross-validation. But when your data set is big, going for n-fold cross-validation, there's no need to do that because it's going to take a lot of time. Dividing 1 million samples to 10 places again, it means you're going to be running the experiment 10 times. The data is already big. Just divide into 3, training set, validation set, and testing set, and then you should be good with your data. But sometimes it's just a requirement by the client that I want you to use n-fold for me, then you have to use it. or you are writing, you're solving a research problem. Someone already worked on that data set using n-fold cross-validation. So since you want to work on the same data set, you have to also use n-fold cross-validation. Even though you find out that the data is relatively big, we can use holdout method. My advice is use the holdout method and also use the n-fold cross-validation that they have used in literature. Because without using what they have used, there's no way you can compare your work with their work. So this is how it works. So for further details on how to evaluate machine learning model, we can refer to some of our videos that we earlier uploaded to our YouTube channel so that we can get better explanation on that. That is how we determine how to break our data into 2 or 3 as the case may be. The next question is, if we have a small data set, like 15 sample, how many fold of cross-validation is I did? I think I've answered this question. So you have 15 sample, maybe 3-fold could be. See, so you have 5 in each of the fold. So you also try maybe 2-fold. So you have 7 in one and 8 in the other one. But yes, because if the sample is very small, you have to use less number of folds. Somebody having 15 sample and using 10-fold, it means some of those fold we have only 1. No, that doesn't make any meaning. So if the samples are fewer, that is why we call it n-fold. It doesn't have to be 10. It could be 5, it could be 2, it could be 3. So the numbers, it could be more than 10 actually, depending on the number of samples you want to use. So, but 15 samples, as the question says, 3 folds should be fine, or 2. For the slide on training and validation, if divided into 2, where are the testing data set? That is, yeah, if you divide into only 2, let me clarify from here, you're only going to have testing data. See, train and testing. But if you divide into 3, then you are going to have validations and testing separately. It means it's like doing testing 2 times. You see, I do it immediately after the training using 15%, and I'm going to do it later also using another 15% or 25% as the case may be. But if you have divided your data into 2, then you are going to have only 1 testing. There's not going to be validation separately. And it's okay. It's acceptable. But if the data is much, it's always better to use 3, to divide into 3 places. Yeah. I think that's some question on that. So what is the magnitude of the data set before it can be considered to be big? So the question also finally arrives. So, well, there's no really yardstick to see that data is big. It depends on the area. In some areas where the data is very scarce, like material science, not enough data set there. So very few samples will be regarded, wow, we have gotten a lot of data. I say, how many data is enough? They say 150. I just laugh. I say 150 is enough because 15 sample used to be the norm, the normal thing we see in published papers there in that area. 15, 17, 25, 20, 27, 30. Now someone has gotten 150. So to him or her, that looks to be a big data. You see, but in other fields, that is insignificant. We're talking of thousands, millions of samples. So that is why it's a relative term, the data that is big, actually. So, and that is why we say, always let the data speak, let the data speak. Yeah. But anything less than maybe 100, then it's better where we get more data samples. But sometimes the data is good, even with very few data samples, you can get excellent result using the appropriate algorithm, simple one like k-nearest neighbor. Use a perfect machine. When your data is few, it has some unique capabilities that made it to forward in the face of few data sets. Now, so there's no really specific magnitude that you can, there's no clear cut when you say the data is big. Yeah, the bigger, the better, but it's also relative term, depending on the area we are working on. Please, can we use weka for optimizing, let's say, neural network for diagnosis? Yes, you can use weka. I think we show us also that time how you can actually select neural network is one of very popular one to do. So you have to optimize the hyperparameters, like the number of hidden layers, the number of neurons in each of the hidden layer. You have to optimize the function, the activation function. We have to optimize the activation function. What is the correct activation function that is going to be good for your data? What is the number of hidden layers that is good for that particular data? And in each hidden layer, how many neurons you are going to use? So these are very important hyperparameter values that we need to optimize when you use neural network for diagnosis for any problem that we want to use it for. It's a very potent and very popular algorithm. However, to use neural network, you need to have sizable data set, maybe in hundreds or thousands, actually. If your data set is very few, personally, from experience, I don't recommend neural network. I recommend k-nearest neighbor, support vector machines, decision tree, and other simple algorithms that could actually work for you. But I've clarified, support vector machine is not simple, but actually, however, it has a unique capability to work on very few samples and achieve better results. Unlike neural network that you need to get sizable number of samples before it works for you. So how do we calculate kappa coefficient after classification? Well, I think kappa coefficient is part of the standard quality measure that often display in weka if you're using weka or any other system you are using. So I show us in the previous video on how to use weka or how to import data into weka using Excel and the likes. You see, once you are modeling your weka, you go to the additional option or more option. So in that particular place, you click it, you can select what are the other quality measures that are not presently being displayed for you, but you need it for your own experiment. You can always include it. And if you are using another platform, whatever quality measure you want to use, including the kappa coefficient you want to calculate it, yeah, it is available in weka. It is one of those tools that are naturally shown to you. And if it is not selected, just go in there and select it, and then it will be part of the result that will be displayed for you after running your experiment. So how do we calculate the variance accounted for after the regression? Yeah, similarly also, once if you are solving the regression problem, you all know that you have the outputs. You see, once you have your output, there's going to be the actual, the one that is given, and the predicted value by the model. So you have them side by side. You can actually extract it to your Excel or wherever you have it. You can even make weka to put it in an Excel file. We display that already for us in our videos, that you can directly ask weka to send your results to the Excel so that you can take it there. Whatever further computation you want to, you can easily do that. We have the variance, we have the standard deviation from the mean, and also other calculation can easily be produced, even though some of them also are made available by the weka package. So can the ML be applied to social science studies, especially in the field of gender and developmental studies? For sure, like we said earlier, so machine learning is coming ubiquitous, it's everywhere. Whatever, any area where you can get your data set out, surely you can use machine learning to solve it. And actually, we look forward to a lot of social science studies because these are some of the areas you can easily make questionnaire. Those your questionnaire, actually, just make them, convert them to data, put them in Excel or whatever format. It's ready for modeling. Yeah. And there's so many other social media data that could be extracted, relate on social science studies, either gender, developmental studies, a lot of issues. This is why personally passionate about the issue of application of machine learning, because there are so many problems, social, environmental. Just think of any problem where you can make use of machine learning to really make life very easy, to preemptively, you see, to preemptively predict if something is going to happen before it actually comes to exist. Because we have some of this data available for us, but because we are missing those things, for example, someone is going to be depressed. Before someone just go into depression and he or she try to commit suicide, it doesn't just come in a day. Science must have been there for long, but no one is monitoring it. No one is doing anything to be able to detect earlier enough and offer the assistance that such people really need. So this is the idea of using machine learning. This data could be gotten either from social media, interaction, and host of other means, so that we can quickly know that, oh, this person is suffering from a particular ailment, either social, psychology, or whatever are the types, so that we can come up with preventive measures, which they always say is better than cure. Prevention is always better than cure. So it's better to prevent someone from slipping into depression if you can detect at very early stage. And I want to believe a lot of social science studies also fall into things that are similar to that, and others that are even outside these kind of examples. But the secret is, once you can get the data set, then you can use machine learning. This is the secret. Once you can get data set, irrespective of the area, is the data set available? If the answer is yes, for sure you can use machine learning. How can you use machine learning? Then you can try to talk to some of the experts you have to come across. With very little guide, you can solve a lot of very, very sophisticated problems that could have affected people negatively if we can use machine learning appropriately, as the case may be. So this is what we're going to use. So we're going to stop the this week engagement, where we're saying specifically, if there is data, for sure, machine learning can surely be used to benefit people appropriately. So thank you very much for listening. So the remaining few data questions, we're going to take it next time, God willing. Thank you very much for listening. So we're going to take a few questions before we call it a day. Once again, thank you, and have a very nice day ahead.